right, Maglab presents Take Two Series Marker.
Hey Brad, good to see you.
Hi Caroline, how are you?
So what are you doing at the Maglab today?
So we're working in the hybrid this week.
Okay, so the hybrid is 45 Tesla, right?
Yep, that's the biggest magnet here.
What are you putting inside of it?
We're putting in a high temperature superconductor.
Okay, I know I've heard of this. Can you talk me through exactly what that means?
Yeah, so a superconductor is something that has no resistance. So a normal metal, when you put electricity through it, it gets kind of hot, like a light bulb filament. Right. Well, superconductor, if it's cold enough, when you put electricity through it, it doesn't have any resistance at all.
That's really cool. I know that there's different types of superconductors. Mm-hmm. What exactly are you studying?
We're studying neodymium-doped lanthanum strontium copper oxide.
That's a mouthful. Yeah. So what does doped mean in this context? Because I think it means something else.
Yeah, it doesn't mean like sports doping or anything like that. So this means we take out one of the elements and put in a little bit of something else. So in this case, you take out some of the lanthanum and you put in a bit of strontium, and that changes the material's properties.
That's really cool.
Yeah.
Is the hope that we get to use superconductors in real life someday?
Yeah, so MRI magnets in hospitals use superconductors all the time. And in fact, the newest magnet at the Maglab, the all superconducting 32 Tesla magnet, that uses high temperature superconductors like this one as an actual electrical conductor.
So what you're studying can help us make other magnets
Bigger
to study
more
exciting things.
Yeah, that's right.
Why does the magnetic field matter?
So in this case, what it's doing is it's sort of giving the metal a reference point. Normal metals kind of have a sense of scale. So if you were standing over a model train set, you would feel really big.
Okay.
So that's your sense of scale.
Right.
So a metal has a sense of scale as well. In most cases, but the high temperature superconductors, they don't have a sense of scale.
They just do their own thing.
They just do their own thing.
And you don't know why.
And we don't know why, and it's really interesting. So we apply a large magnetic field, which sort of gives them a reference, a sort of sense of scale, and then we find out how they behave.
And this is something you couldn't do at a lower field.
That's right, we need the DC magnet, and so that we can rotate the sample very, very slowly in a fixed magnetic field.
That seems really complicated.
Yeah.
Well, thank you so much.
Thank you.
With this activity, how we impact society with the activity that we are doing here. Okay, so, but let's go to first.
Yeah, so we're at the hybrid this week, and we're trying to measure the Fermi surface of neodymium-doped LSCO.
So why did you choose neodymium-doped?
Because TC is so low in this material, we can actually get to the normal state in the hybrid at all angles without going to very high temperature.
So what would be the residual resistivity of this thing?
It's in the C-axis, it's about 25 milliohm centimeters, but in the plane, it's only tens of microohm centimeters.
Independently of the doping level?
It's actually pretty independent of doping level.
So you expect the Fermi surface to go 2D, and what happens when it breaks apart?
Well, that's the question. Yeah, we don't know. Yeah.
So let's go for the intellectual merit of this activity.
Yeah, so we'd really like to know what the Fermi surface does across the whole phase diagram of the cuprates, because we want to know what's giving rise to superconductivity. And the big challenge is for the really clean materials like YBCO, TC is just too high, and we don't have the magnets to get there yet. We need 200 Tesla.
And what would be the broad impacts of discovering and understanding the fermiology of high TC superconductors?
Yeah, so hopefully that gives us the ingredients to actually construct a new type of high temperature superconductor. If you really understand what the relevant types of Fermi surface reconstruction are and where in the dome they're happening, then you might have some idea of what the ingredients are. Is it spin pairing? Is charge density wave important? Or is it hurting? That kind of stuff.
So it seems that we are probably running out of time. So if you need more information, you just need to follow this link.